Hi, everybody. All right, so we are starting on chapter 17. We've actually, in class, by this point, have spent a couple of days learning about elements and working on memorizing names and symbols. And I want to go actually start now on the chapter with you all as far as some of the history of the periodic table, some of the people who kind of got it to where it is. Personally, and I know it sounds super geeky, but I truly believe that the periodic table and organizing it and the things that we can learn from it, are one of the greatest discoveries of modern science. It's just super cool. Okay, so anyway, starting out, so organizing the elements, we have several men who, after a number of elements had been discovered, uses, my nose is itchy, characteristics, all those kinds of things, decided that they needed to have a system of organization so that it all just made a little bit more sense. The first one is a man named Johann Dobereiner. And his contribution to organizing the elements was that he classified elements into groups of threes called triads. And he did this based on similar properties. And that could have been state of matter or how they reacted to another element, or if they dissolved in water. I don't know, but he was just looking at basic properties. He gave it a try. He wasn't real successful in convincing other people because not all the elements fit into his system, and so it just was maybe a little bit too limited for all of the elements. The next man, he is French, which means I will not try and pronounce that name, but I do know that the AE stands for Alexandre Emile, and he was a geologist, I believe, knew a lot about minerals, and he graphed the elements by mass. And so that picture there just shows a little slice of one of his graphs. And he noticed that when the graph was rolled into a cylinder, every eighth element had similar properties. The rolling into the cylinder, I don't know if that was a trend at the time. I don't know if that was a well-used process or if it just kind of happened, but that was kind of the start of this group of eight. Okay, so the next one, John Newlands, he arranged the elements by atomic mass. Remember, atomic mass is the protons and the neutrons of each atom added together. And he did this, and he noticed that every eighth element had similar properties, and he called these groups octaves, so similar to music, octave, every eight. And he then took the 49 known elements and he put them into rows of 7 and had them organized in ways that the similar elements were kind of lining up. And he called this system the law of octaves. Okay, so now this next guy. I know he looks a little suspect, but he is actually known as the father of the periodic table. He kind of took what Newland has done and he arranged the elements by atomic mass, and then he did the same kind of column thing, and then he grouped elements with these similar properties, again, mostly based on how they were reacting. And then he placed the columns next to each other and formed rows. He noticed that there were times when he needed to leave blanks for unknown elements in order to keep the rows and the columns kind of standard with elements having similar properties and increasing atomic mass. So he realized we were missing some information based on how obviously related some of those elements were. Mendeleev, sorry, I'm mixing up biology here. Mendeleev thought he could use those blanks to predict new elements, and quite a number of those elements were discovered because people were looking for them specifically based on his table. his table, the reason we call it a periodic table is that the properties of the elements repeat in a periodic fashion. So, you go back, kind of, it's a cycle that you can go back through as you run through the rows or the columns. And so, so they periodically repeat themselves. And Mendeleev called this the periodic law. One problem with his table was that some elements didn't quite fit, like they were just, if they were switched with the element next to them, then everything would kind of work out better. So Henry Moseley, kind of our last big guy, he took Mendeleev's table and did that. He switched some of the elements, and he realized that if he switched them, then he would just basically be arranging the elements by their atomic number, so strictly by the number of protons. And he basically revised that periodic law and said that those chemical properties that we see repeated in elements are functions of their atomic number. It is one of the clear pictures of God's orderliness. If you look at how well the elements fit, if you look at the patterns that you see in the periodic table, but also within an individual element and its atoms, it is clear that that God had a plan when He created things, and that there is so much structure in His creation. And so so there's this little picture here of Moseley's table. Again, there's some differences, and there were still some unknown elements that that needed to be discovered, and but it's kind of starting to look a little bit more like our periodic table. Okay, so now, of course, the periodic table was tweaked, and it was rearranged, and you had different parts put kind of, in different columns. And of course, now it's not, like a table, like, squared off or anything. You have different heights and different columns, and that comes just from knowing more and more about the elements. But in general, Moseley and the guys before him were, the ones who figured it all out. Okay, so anyway, groups on the periodic table, or areas on the periodic table. First off, the metals are on the left side of the table, and I typically describe the dividing line as the stairs or the zigzag line, and it's a darkened line on our periodic table. When you guys colored your own periodic tables, I had you darken it, and that's the dividing line. And so metals are to the left of that. So the majority of the table is metals, about 3/4. The chemically most important thing about the metals is that they have a small number of valence electrons. Remember that valence electrons are the outermost electrons. So when you filled in the dots, or when we did the X's on the circles, the very last circle that got stuff filled in or X'd, those were the valence electrons. And so typically metals have 3 or fewer valence electrons. Common characteristics among them, they have a luster, which means they are shiny. They're solids at room temperature. The one exception to that is mercury, which you should know. Its symbol is Hg. They are malleable, which means they're easily shaped. So think about like aluminum foil. Ductile, which means if you kind of twist and pull, you can pull them into a wire. They're good conductors of electricity and heat. Again, things that you know. And then this last one, they're reactive in chemical reactions. That goes back to those valence electrons. Okay, so now on the other side of the staircase, those are the nonmetals. The two big groups in there, and we'll talk more about these in a minute, are halogens and noble gases. They have a higher number of valence electrons, so typically up to 4 valence electrons, or excuse me, 4 or more. Hello, and again, that it contributes to how they react chemically with other elements and to form different compounds and whatnot. Common characteristics, again, they don't all have these characteristics. No luster, so they're dull in appearance. You have a variety of colors. You also have all three states of matter at room temperature within this class. Um, the gas state is the most common. The periodic table in our room, the gases are in red, and so if you think to look when you're in class, that the right side over there, you got a lot of red elements because those are the gases. If they are solids, they are usually brittle crystals and they shatter very easily. They're poor conductors, and then they tend to gain or share electrons in chemical reactions. And again, that's part of how they react. Okay, metalloids. These are elements that are touching the stairs, like they have at least one side on the staircase, either above or below. The exception is aluminum. But these are elements that have properties of both metals and non-metals. And they're kind of their one big useful property, I guess you could say, is that they're slightly conductive. So they are considered semiconductors, a lot of them, which means they're poor conductors at room temperature, and they are actually better at conducting at higher temperatures. This makes them really useful in electronics because electronics heat up as electricity runs through them. That's just, how it works. And if they're not semiconductors used, the metals tend to be poorer conductors. They tend to not do as well allowing electricity to stream through them. And so the discovery of semiconductors and then their use has been a huge advantage in a lot of the technology that we are using today. Okay, so now columns. So on the periodic table, the columns sometimes are referred to as families. And there are a couple of things about columns that, or one main thing, I guess, that you need to know about columns, and that is if they're in the same column, they have the same number of valence electrons. And I'll kind of clarify column in a minute. But so, for example, column 1, all the elements in that column have 1 electron in the outer level. Column 2 have 2. And remember, these valence electrons are extremely important in the chemical and the physical properties of elements. So they're very similar to each other, and that's where they get the name family. Just like you are similar to your siblings or your parents in some way. These elements are in the same family, and they are similar in some way. But again, there are exceptions, and there are also differences. Okay, so going through the groups, and typically we'll go through the groups and the family, as the tall columns is what I usually refer to them as. And so if you are in the room, you know what I'm talking about, because there are 2 tall columns, and then you have some shorter columns, and then you go back up again. We will talk about the tall columns. So very first column, its name is alkali metals, and they all have 1 electron in their outer energy level, like I said. These are highly reactive metals. They react violently with water and oxygen in their pure forms. They have to be stored like immersed in oil, so they don't react with oxygen in the air. But they are very common and very stable in some common compounds. Sodium is Na. It is in sodium chloride, which is salt. And so that's just one example, but our body is very reliant on some of these, reactive alkali metals in compounds like sodium or potassium, because they help our cells do the things that they need to do. They help us move water around in our bodies, which sounds kind of weird, but on a cellular level, big deal. They help with nerve impulse transmission, muscle control, all this kind of stuff. If if your muscles cramp a lot, it's because you don't have some of these minerals to help everything move around correctly. Okay, group 2, so this is the next column. The top of this column is Be, beryllium. These are the alkaline earth metals, 2 electrons in their outer energy level. They're slightly less reactive than the alkali metals. They're not quite so explosive, I guess you would say, in pure forms. They also, though, are found in lots of common minerals. And I've listed here on this page some of the uses, and you guys may have some additions to these if there are elements that you guys looked at for our periodic table. But they notice how different their uses can be, one to from one to another. But be aware that physically their atomic structure is similar. Beryllium is a very light metal that is used to strengthen other metal alloys. That just means you mix it with another metal. Magnesium, Mg, is another lightweight metal. It's used to make the stuff that they make airplanes out of, the metals. You put it in like laxatives. It can be in like stomach medicines. So wide use for that one, and your body enjoys magnesium. Calcium, of course, you guys have all, I'm sure, heard of. It strengthens your bones, your teeth. They also put it in a lot of concrete, plaster. Barium is a radioactive substance. You use that, or you can use this in x-rays. It helps to x-ray soft tissues. Some of you may have had to have an x-ray of like your esophagus or even your stomach if you've had stomach issues, and you drink what they call a barium milkshake. It tastes a lot like chalk, which makes it similar to calcium if you've ever had pure calcium, but it helps with that. Strontium, I kind of have those out of order, sorry. Strontium is above barium on the table. Oh, and I even skipped one. Anyway, let me finish strontium. Strontium is Sr. It is the red color in a lot of fireworks. And then radium. Radium is Ra. It is used, or was used, in luminescent paints, like the stuff they put on like the roads and the lines on the street. Before they realized it was really dangerous, they would use it on a little more common items, but it is radioactive, and so it can cause issues. And so some of these, strontium, going back to that, sorry, I'm kind of off order here. Strontium is dangerous in some radioactive decay reactions. If you're exposed to it, your body takes it in, but because it is so similar to calcium, your body puts it right into your bones, and then it continues to decay in there, and then can cause real structural damage. Okay, sorry for this small page. I think I was just trying to squeeze stuff in. So now we're going to jump over the big gap on the periodic table to the next tall column. Oh, hang on, let me go back, read my notes while I'm talking about them. Groups 3 through 12, the very top thing on this page. These are the short columns. These are typically called transition metals, and they're transition because the number of electrons in their outer shell has a tendency to change. Transition means change. And these are mostly found in alloys. Most pure metals are too weak to be of much use, or too soft, and so when you mix them and form alloys, you have very strong metals. So that's what they use for a lot of these guys. Now, the next tall column, boron is the top element in this family. Typically, it is called the boron family. Boron is the head of that family. This, you have metals, aluminum and boron are very common, and they are, again, kind of above and below that line, and so you have the semiconductors, kind of the unique structure that they have. Aluminum, just my little fun fact there, is the most abundant metal in the Earth's crust, so it's very common. Like, we just think of aluminum foil, but it's in a lot of other areas. Then the next column is column 14, and it starts with carbon, so that's the carbon family. You've got carbon and silicon, and those are best known for lots of the compounds that they form. Every living organism has lots of carbon in it, because it is big components of our cell walls, cell structures, all that kind of stuff. Germanium is Ge. It's a semiconductor, used as a semiconductor. Pb is lead, down at the bottom of that column. It's used in batteries. It's shields against radiation. We talked about that, like the vest they put over you when you have like an X-ray. It's a very dense metal. And then group 15 is the nitrogen family. You've got nitrogen, which first of all is a gas, and it is the most abundant part of our atmosphere. I should know for sure, but I'm pretty sure it's about 78% of what the air is around us. We tend to be just like, I'm just breathing oxygen. You're not. You're breathing a lot of other stuff. And nitrogen is in our atmosphere mainly to keep the oxygen stable. And so we breathe it in, but it's also necessary for plant growth. Lots of phosphorus is also needed. You see those in fertilizers. And then kind of interesting, right below that, you have arsenic, which is a poison, which you don't want. Antimony, which is SB, that is a semiconductor. Bismuth is BI down there. It's used in cosmetics. It's also used in stuff like Pepto-Bismol. That's where that comes from. And so you have, again, all in the same family, you have poisons and medicines. And so, again, there are major similarities, but I'm kind of pointing out some of the differences. Okay, group 16, this is the oxygen family. Obviously, oxygen's a big deal. It's essential for life. You breathe it in to keep your cells going, and of course, they keep you alive. It also forms our ozone layer, which is protecting us from some of the radiation from the sun. Right below oxygen is sulfur, which is used in like large-scale industrial manufacturing. If you go down to Galveston and drive around kind of like in their industrial section, I don't really know why you would do that, but if you did, you would smell the sulfur and maybe even see like big piles of like a yellowish, well, it looks like a rock, really yellowish substance. Selenium is Se. It's used in semiconductors, solar cells. Tellurium is toxic to us, but it can be used in semiconductors and alloys. Again, strengthens other metals. Polonium is the energy source for like deep space probes, stuff they just send out to take pictures, and then it just keeps on going. But the polonium is the power source for those. Then the 17th column has its own special name, and those are called the halogens. And they're very reactive chemically. They tend to form lots of compounds. The chlorine in that column is the other half of sodium chloride, the other half of salt. This is the only family that has solids, liquids, and gases in it. And these tend to be very dangerous at high concentrations. Chlorine by itself, pure chlorine, is actually a poisonous gas. I know you guys all have been to a swimming pool that has a real strong chlorine smell to it, or it burns your eyes. It does help to disinfect water, so it does help to kill bacteria in that pool that you and everybody else are swimming in. Fluorine is in a compound added to toothpaste. A lot of times it helps to strengthen your tooth enamel. Iodine has lots of uses. I put on there prevents goiters. A goiter is a growth that you would see on your thyroid gland, and your thyroid gland happens to control your metabolism and all that kind of stuff, but it also somehow processes iodine in your body and helps to prevent these growths. They used to be really common in the US, and I'm sure around the world. So one of the reasons that when you buy salt, it is typically iodized salt. They add iodine to it, and then you eat it, and it helps your thyroid not to produce or grow these goiters. Okay, last column on the periodic table are the noble gases. They are sometimes called the inert gases. They don't combine with other things. They will not naturally form compounds. Very much like the noble gas, the noble class kept itself apart from the common people. The noble gases keep themselves apart from the other elements. So that's where that name comes from. Helium is used in a lot of things, used in hot air balloons, or the balloons that you guys just like buy on Valentine's Day. Neon, xenon, those are in lights, signs. Argon is a lot of times used in welding. They're very stable elements, and so they're used in a lot of these areas where they may be exposed to different energy levels and electricity and that kind of thing, but they are inert. All right, and then that last little part, you can read that. If you need to know the number of valence electrons, look at your numbering. Okay, so now almost finished. So we've done the columns, so now the periods. The rows on the periodic table are called periods, and the elements in the rows do not have similar properties. As you go across, the atomic number will increase. As you go across, you go from metal to non-metal, and what the rows can tell you, one of the big things, is the number of energy levels, or like when we did the circles that the element has. And so if I told you, to tell me how many energy levels sodium has, it's in the third row, so it has 3 energy levels. Your book mentions this. Sometimes rows are called series. That's not super common to me, but I want you to be aware. Okay, last page, some periodic trends. The properties of elements, remember, are determined by valence electrons. And the valence electrons, their location can tell you how far it is from the nucleus, and this tells you how strongly the electrons are held. And that's a big deal because elements tend to give up their electrons when they form compounds, or they share or transfer. And so knowing kind of what the valence electrons are doing or where they are can help you determine how reactive or even what kind of compound that element might be found in. So with this electron, valence electron arrangement, there are a couple of things to know and a couple of ways that we'll represent them. The first, if there are paired electrons, they tend to be more stable than single electrons. They kind of keep each other in line if they are together. And then the second, we typically represent valence electrons by what they call electron dot notation. And this is where you have symbols with the dots that represent these valence electrons. And so we'll do this in class, but if you're looking at row 2, starts with lithium and then moves on across beryllium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. As you go across, you basically add one more dot until you get up to 8. 8 is the total number of valence electrons that are possible. That will be one of the things that we additionally label on our periodic table. So kind of look for that and make sure you get that, and I'll tell you what to do when we're in class together. I'll tell you exactly where I want you to put some of this stuff. Okay. Then there are things called periodic trends. There are several trends that are noted. I've just got 2 of them on here. The metallic properties, first of all, decrease as you move across a row. So that's a trend. As you move across, it tends to become more non-metallic. So you see that play out. Also, the atomic size increases, so the atoms tend to get bigger as you move down the column, which makes sense because remember, as you move down row by row down a column, you are adding one more energy level as you move down a row. And so you add more circles basically, and so that atom gets bigger. Oh, okay. So that is the periodic table, one of my favorite things in science. We will do way more with it as we talk about naming. When you guys take chemistry again in a couple years, we'll go into even more depth about it and the uses for it and what it really, some of the things that it can tell us. So ask me questions in class, and I'll talk to you later. Bye, guys.